Hello everyone, my name is Rozumnyi and I'm a master's student here at CTU, and I'll be presenting my project on fast moving object. I've been working on this project for almost 3 years. So I started as it was an internship in Finland with my supervisor, and then I continued as a bachelor thesis, and we actually continue. We have grant stipends for this project, so I'm finishing my master thesis. And all right, I'll show you it's a collaboration of several people, and yeah. So what is a fast-moving object? First, it's an object which moves over a distance which is larger than its size in one image frame. So you can see here some examples. They're quite common in sports, and it's a new problem. We had the first publication at a conference 2 years ago, and nobody was interested in this problem before in computer vision, but actually it was shown that there are a lot of interesting applications. For example, we can measure the object speed, and we can detect its appearance just from blurred frames. And there are also applications in astronomy or other sciences, or automotive cars. For example, if there is a stone coming into your car, you can actually detect it and do some action. So what are our goals? We would like to detect all fast-moving objects in videos. Then we can track them. For example, if they disappear or reappear, so we would like to find all the trajectories. For example, for sports, it could be interesting to, for example, we already have an application for Android where you can just put your phone and it will detect the trajectories, and you can post-process them and find interesting information. And then we can, because we know the exact mathematical definition of how they appear, we can do the blurring, mathematical applications, and detect the real object model. And then we can calculate speed, size, and do some super resolution and so on. So I'll formally introduce the problem. So the image is formed if you have an object of, for example, F and M, you can see it here, and some background B. It's basically a convolution of its trajectory with F and plus some amount of background, because you see less of background, and then you can, so this is our model, and when we do deblurring, we basically want to reverse this mathematical formula. And so how do we define the convolution in this case? So basically, it's just a path, it's a trajectory of the object, and its model convolution, then you divide it by the size of the trajectory, so that it sums up to 1. And this equation is satisfied only in the case when there is no rotation or the object is homogeneous. But usually you don't have to have exact, and it's enough to have an approximation of this assumption. So when we started this problem, it was interesting that in standard tracking datasets, you don't have any fast-moving objects. Usually when people do tracking, object tracking, they have just small motion, or if the object is faster, they will just use a faster camera, high-speed camera. Nobody cared about very fast-moving motion because they basically disappear. They're so blurred. And for example, here you can see histograms of object speeds. For example, on the left side, it's basically, you see that standard tracking dataset, they have speeds less than 10 pixels per frame, and we introduced a new dataset which would cover all the range of speeds from 0 to 150, and this is the intersection over union. Basically, it's a measurement how they far away from each other, and you can see that we introduced a new dataset which is quite different from the others. So this is how the dataset looks like. It's an annotated dataset, and it contains usually sports, but I think only sports in this case, but then we had version 2, and we introduced even more. And you can see they're quite blurred, and we have ground truth for that, and I'll show you the results in the next slides. There are also some videos from YouTube, so they're quite diverse. And now I introduce the method. So first of all, I said that we would like to detect all fast-moving objects in every video frame. And for that, our method is based on a difference image. So first of all, we have to find a background. And it's interesting that if you take a median of previous, for example, 3 or 5 frames, it would remove all fast-moving objects, because due to the definition, it moves over distance larger than its size. So if you take a median of image frames, then basically it would appear only once in, for example, 3 previous frames, because it will be on totally another position. So you can see here that frame like time t minus 2, minus 1, and this time, and if you take a median of these 3 frames, you would just get the same image frame but without fast-moving objects. And the next step would be from the background image and our current frame, we would compute the difference image. And you can see here that there are a lot of different other motions in they are like connected components. And what we do next is that we try to deblur to find the connected components which satisfy our model. I already introduced you the convolution and summation of background. So that's basically what we are trying to do. We are trying to mathematically explain, if we could explain this connected component mathematically with that model. And for that, we have many unknowns. We have trajectory, we have object f, which is how it looks like model. So background, we already have background, so we have at least 3 unknowns. We cannot estimate all of them simultaneously. So the first step is to try some initial trajectory. And in our case, we are trying to compute the local maximum of distance transform, which is basically all the pixels in the middle of this connected component, and then we are fitting curves to find the initial trajectory. So this is the first step, and then when you have initial trajectories, we are iterating of estimating object appearance and its trajectory. So here on the first, you see just the inputs, image and background, and then this is the initial trajectory. And then we apply the iterative deblurring, and we found, for example, several. In this case, the first one is true positive. It's what's really a fast-moving object, and you can see the trajectory, and nicely you see the ball with illumination. And in the second example, see this is just a shadow, so it's not a fast-moving object, and you can see that the trajectory doesn't look like a real fast-moving object. So how to check this? So our method is based on just fitting. We are trying to fit polynomial piecewise functions. And in the first case, you can see that you can actually by hand nicely try. You see this is piecewise linear function. It's easy to fit. But in the second case, fitting would fail, and that's how we detect that. And after that, when we have all the unknowns, for example, f, the object model, trajectory, and so on, you can basically try to synthesize our model. So, for example, if you take the background, downscale it, and add the convolution of trajectory with object model, you would find the same as the input image. So this is not the input image, it's just synthesization with all the unknowns. And so this is what we introduced 2 years ago, basically, and this is something new which I'm working on now. It's tracking by deblurring. So when you have all the unknowns in one frame, you don't want to do it in the second frame independently. You would like to do some logic inside this. And we created some mathematical model for this. So if you have a trajectory, you can easily predict where it would be in the next frame, but just approximately. And then you try to do the same, but you just have some initial trajectory from the prediction. And this is basically a minimization problem where the first data term is just fidelity to our model. So you have the image I, and this is what it should be, our model, how it should look like, and you're trying to minimize the error. And then there are some terms to minimize the smoothness, that the object is smooth and trajectory is sparse. So you can see here that when you try to do that, you have some gaps, so there are a lot of noise. But that's why we have fitting step, which is basically we force it to be a curve. So you can see that it can be, for example, parabola or piecewise linear function. This is usually all we have. And this is the whole pipeline that you have motion prediction or detector, fast-moving object detector, basically 2 steps. If there was some detection in the previous frame, you just do prediction, and then you update, do the blind deblurring of this is the trajectory, and F is this object model, and you estimate them until it converges, and then you do trajectory fitting, and you predict it to the next frame. So you track it in the next frame and in the next frame, and that's how you have the full trajectories. And this is in trajectory fitting, you have consistency check, that if you cannot fit anything, like in the previous example with shadows, that you have basically a lot of noise in the trajectory, fitting would fail, and you detect, no, there is no fast-moving object, and then you would wait for the next fast-moving object detection. So this actually, it was shown that this method, tracking by deblurring, allows for tracking in all speed. That, for example, if your object slows down, fast-moving object detector wouldn't find it. And this method, tracking by deblurring, allows for tracking in all possible. For example, if it's still or slow, your trajectory would be just 1 point. Or if it's very blurred, you would have long trajectories. So this is what we showed, that this is a FEL detector which performs well for large speeds, but then it failed because the difference image, if it's very blurred, difference image wouldn't find anything. It would be just almost zeros. And standard tracker performs well for lower speeds, and then it's worse and worse. And we showed that tracking by deblurring allows basically nice performances in all range of speeds, from still objects until very, very blurred. And now I'll show you some applications. So when you do deblurring and try to estimate the trajectory function, you actually, inside this function, you have information about the object speed. Because if object stays longer there, you'll have more value in probability spread function, and that's how this is an experiment, how we estimate the speed in pixels per exposure time. So in one frame, how many pixels the object elapses. And dashed line shows the ground truth from high-speed camera. And in this experiment, actually, it was shown that our estimate is quite precise, as you can see. So it allows for intra-frame object speed. Usually when you just do tracking, you have from one frame to another at 30 frames per second. But with this method, you can actually find the speed, for example, at 2.3 frames. So it's something in between, on the second frame, third frame, but with much more precision. And then we tried evaluation on just different data sets, different videos, and you can see that it works pretty well, for example, on sparks or firestorm, or just fallen objects. For example, if some cherries or apples fell down, you can count how many were there, or for example, hailstorm as well. I'll show you some videos later. And this is the results on our data set. You can see frisbee, tennis, ping pong, table tennis. So it works pretty well, but there are some gaps, and that's where it failed. Just more YouTube videos where it worked. And so another interesting application, as I said, is when you have object appearance F and background, you can basically estimate super resolution. For example, if you have original video of 30 frames per second, and you would like to have much faster video, which would show some precise locations, you can basically estimate it. And this was the ground truth from high-speed camera at 240 frames per second. You can see it's a little bit blurred, because even at this high camera speed, there is some blur. And this is in the bottom row. This is our estimate, which is basically a background plus object appearance F, which was estimated by the deblurring. And you can see much more details. And what is interesting, that this bottom row was generated just from the input frame, just from this one frame. And you can see from that frame coming here, it's almost impossible for humans. You cannot say what's written on the ball. And from this, you can already see that it's Mikasa. You can see that there is some noise. It's not very realistic, but it's still impressive that how computers can beat even humans, because you see this frame and you cannot tell what's written there. Yeah, you can see it in more details from here to there. That's what we can do. And there are even more applications. If you can input, like insert some high-speed camera images, you can insert anything basically. You can replace the object. So if somebody is playing this ball, you can change its color and generate the same video with the same object but of different color or of a different object. So this was the input frame, and this is what we just changed. And we can increase the size of the object and anything. And I'll show you some videos now. So this is just the detection of fast-moving objects. So you can see it works pretty fast, and so it's in real time, and we can detect even more objects. It was 5 fast-moving objects. Or we can remove them, so they're playing with no ball. So this is basically the background estimation, and with removing the object. But you can see here you could see it there, because it wasn't a fast-moving object here in the right side. It wasn't a fast-moving object, and that's why it's there, because we remove only fast-moving objects. This is firework detection. It's much more difficult here, but it still works for some of them. Hailstorm. A lot of them were missing, and the camera was moving, so it's much more difficult. Sparks. You see, some of them are so small that basically just several pixels in the video. The blurring would fail there. And this is temporal super resolution. So original image, it was so quick, it was just like several milliseconds. This is slowed down just by interpolation. And this is our reconstruction, so you can see smoothly how the object moves. And you can see again how it looked in the original frame. It was just like this. And if you want to see some precise details of the object trajectory, that's what would we apply this method. So it's nice maybe for post-processing. Right. So I showed you the demos. Do you have any questions? I think this is all. Thank you. Okay, sure. So originally I'm from Ukraine, and I started learning Czech language when I was in my last high school class, and yeah, then I came here on also Czech language classes, and then I was accepted, fortunately. And then I started working in a center for computer vision, for machine perception at the faculty. That's where I started working on a similar project. And first 2 years I was working on something different, for like in pattern recognition, but it was also part of computer vision. And then I started working with another professor, and he asked me if I would like to go for an internship in Finland. And that's where I started working on this problem. And it's been already 5 years, and if you want to come here to study, it's basically you need, I think you know, language and math exam. And yeah, now I'm accepted into a PhD program in Switzerland, and I think this is my next step. But I think good luck to you into try. I think it's English. In our group, computer vision group, it's so international. There are so many people. I think we talk usually just in English. So if you study in English here and you want to find some job in the field, you can easily come into our group. And if you would like to work on machine learning, computer vision, I think it's very interesting. It's the new field. Yeah, so I had done several Erasmus. It's exchange program. I think you should know. I was in Germany, uh, in Britain for 1 semester in Germany, for 1 semester in Britain, in Finland 2 summers, and also in Zurich for an internship. And thanks to that internship, I was accepted into a PhD program there. So I'll go there. I'll graduate, like if it happens and graduate in 1 month, then I'll go there. I think there are so many opportunities, so many exchange programs if you would like to travel. If you have any questions, I'm still happy to answer. And thank you, Lut.